Chapter 4.4, Perform Computations in Other Bases. So in this chapter, what we're going to be exploring is, now that we know how to convert into other bases, how can we do the type of operations we know how to do in base 10 when we're in base 5 or base 7 or base 16? How can I do addition, subtraction, multiplication, division? How does that work in other bases? So we'll start with addition, the easiest one. To add in other bases, we can create an addition table for each base. So in base 2, for example, we want to think out, we're going to have to do a lot of conversion to create these tables. So 0 plus 0 is still 0, 0 plus 1 is still 1. But 1 plus 1, this number here, 1 plus 1, yes, that's 2, but what is 2 in base 2? Well, here's where we're working with low numbers, so quite often we can do this conversion in our head. The question is, how many 2's until I get to 2, and what's left over? So how many 2's is 1 2 with 0 left over, which is how we get 10 is our 2 in base 2. Then for a base 4 table, we get, well, 0 plus 0 is still 0, 0 plus 1, 0 plus 2, 0 plus 3. Those are all fine. Everything's fine until we get up to, for example, 3 plus 1. 3 plus 1 is 4, but what is 4 in base 10? In base 4? Well, 4 in base 4 is 10 because, again, it's how many 4's until I get to 4 and what's left over? Well, it's 1 4 with 0 left over. 1 0 gives me 10. Now this is 2 plus 3 is 5 in base 10. So 5 is 1 4 and 1 left over, which gets me 11. Right? So we can also think of it as 4's and 1's, right? So it's 1 4 and 1 left over. Multiply 1 4 plus 1 1. So what's 12 then? Well, that's 3 plus 3 is 6. So 6 in base 10 is 1 4 and 2 1's. 1 4 and 2 left over. 12. Then base 5. How can I fill this table out? Well, again, we get 0 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2, 3, 4. These are all nice. We can fill these in without too much problem. I can fill in anything up to, but not including 5. So 1 plus 1, that's fine. 2 plus 1, that's fine. 3 plus 1, totally fine, right? Same thing over here, and then 2 plus 2 is 4, and here's where we get, where things get tricky. Notice it's the same problem here. It's the number right under the base, because we can only use digits up to, but not including the base. So for base 4, we use the digits 1, 2, 3, and 0. For base 2, we use 1 and 0. So base 5, it's 1, 2, 3, 4, and 0. We can see that along the side. So once we get to 5, all of these numbers should be 5 in base 10. 4 plus 1, 2 plus 3, those should be 5. How do we write that in base 5? So it's how many 5's and how many 1's? Well, 5 is 1 5 with nothing left over. So this will be 10 in base 5. Then next we have the 6's. So 6 in base 10 is 1 5, and what's left over? 1 is left over, so this will be 11. Then 7 in base 10. Again, it's 1 5, and then what's left over is 2. There's 2 left over, so now this will be our 12. And then finally, 4 plus 4 is 8 in base 10. So 8 is 1 5 and 3 left over to get 13. So altogether it looks like the following. So having those tables can help us do addition. I will show sort of two methods of this, but if I want to add 34 base 5 plus 23 base 5, we add up and down the same way we do with like long addition in base 10. So 34 plus 23. But what I want to keep note of is I start by adding 4 plus 3 like normal. 4 plus 3 is 7, but I'm not going to use the number 7 because 7 is not part of base 5. All numbers have to be 0 through 4. So what I need to do is convert that 7. And having the table can help us do that conversion, but you won't always have the table in front of you, so it's good to be able to do the conversion on the fly. But for right now, 3 plus 4, I can just look at the table and say, 3 plus 4 is the 12. But we can also just say, okay, well, what is 3 plus 4 is 7 in base 10, which is 12 in base 5. So now I say, okay, 3 plus 4 is 12, so I have 12. The same way I would in normal addition with base 10, I put the 2 at the bottom and I carry the 1, like so. So then when I add the next column, I'm adding 1, 3, 2. So 1 plus 3 plus 2. Well, again, I can use my chart to do this addition, or I can sort of think it out and convert it on the fly. So with the chart in front of us, 1 plus 3 is 4, and then 4 plus 2 is 6, but 6 isn't in base 5, so it's 6 base 10, but what's 6 base 10? We can see it on the chart, it's 11. So it'll be 11 in base 5. Again, we can just do what's 1 plus 3 plus 2. Together, that's 6 in base 10, but then we need something in base 5. Base 5, it's going to be how many 5s and how many 1s, how many left over. To get to 6, we have 1 5 and 1 left over, so it's 11. We can do that math as we go. I have the chart in front of us just as a visual representation of what we're doing and something to guide us, but most of the time you won't have that chart, and you won't want to make an entire chart to do just a simple addition problem. So, you'll have to learn how to do that conversion as you go, but at least we're converting in very low numbers because we're working with just the smallest numbers we can, 0 through 4 in this case, right? So we're only converting things that we can basically do in our heads. So now, when I add all of this together, I get 11, and there's no column to carry the 1 to, so I just put the 11 there like I would in normal addition. And so my answer ends up being 112 base 5. And again, we want to make sure this is accurate. We could convert 34 and 23 into base 10 and then convert 112 into base 10 and make sure it actually adds up, which I will do briefly just as a show. I'm not going to do this for all of our problems in the future, but this is just something to show that this is accurate and this is another way we can go about it. So 34 is 3 5s and 4 1s. So 34, we go 3 times 5 plus 4 times 1, which equals, so 3 5s is 15, plus 4 is 19. Then 23, again, 5s, 1s, so that's 2 5s is 10, plus 3 1s is 13. And we're adding these together, 19 plus 13 is 32, so we're hoping this is 32. So this will be the 1s, the 5s, and the 25s, because it's 5 squared, so we get 1 times 25, so 1 times 25 plus 1 times 5 plus 2 times 1. Together, 125 is 25 plus 5 is 30 plus 2 equals 32, and that checks out. So it still does work. We can do conversion. In fact, I could do this conversion, find that this is 32, and then say, well, what is 32 in base 5? And I could do the conversion there. So it's a roundabout way of getting there, and it's not necessarily the way I would recommend doing because it takes a bit longer, but it is another way we can get to our answer, because 32 in base 5 is 112, and it is the same number. Now, let's try out some subtraction. So subtraction can be formed in other bases, again, similarly to how we do subtraction in base 10. But the main problem that can occur is when we borrow. So when you borrow in base 10, you think about, if I'm in base 10 and I say, 12 minus, or let's go with 112 minus 1 minus 19, right? So 2 minus 9, I can't do that, so I borrow, make this a 12, bring this down to a 0. 12 minus 9 is then 3, and yada yada yada, and then now I have to borrow again, make this a 10, make this a 0, 10 minus 1 is 9, and so it's 93, and that's how we do it in base 10. We borrow 10, because what we're really doing is, I took the 2 and I added 10. This number goes down by 1, which is kind of like subtracting 10 because of its place value. So that's what we're going to do here, except it's not going to be 10, it's going to be the base. We borrow the base. So if you're subtracting in base 5, when you borrow 5. If you're subtracting in base 12, when you borrow 12 instead of 10. So here we're working in base 12, so we need to make note of our letters. And so when I subtract, I take a minus 8, a being 10 minus 8, that's just 2. That one's simple. I can just do that immediately. I don't even have to do any conversion or anything like that. It's just 2. But when I do 7 minus b in my second column, 7 minus b being 11, is negative 4. So that's a problem. So we're not going to put negative 4 there in the same way that we wouldn't do that when doing normal subtraction. Instead, what we'll do is we will borrow the base. So we knock down the 9 and add 12 because we're in base 12. So we borrow 12, this becomes 7 plus 12 is 19. So it doesn't become 17 like it would when we are subtracting in normal base 10 numbers. It becomes 7 plus 12 is 19. Then 19 minus b, or 19 minus 11, is 8, and I can just place the 8 right there. And then the last column, remembering that we knocked that 9 down to an 8, 8 minus 4 is just 4, and so we can just finish out with 4, 8, 2, base 12. So again, the main thing to remember in subtracting, most of it is nice. We don't actually have to do any conversion. It's just general subtracting. And if all of our top numbers are bigger than our bottom numbers, everything works out nicely. We don't even have to think about the fact that we're in another base. But as soon as one of these top numbers is lower than one of the bottom numbers, we have to start borrowing, just like we do in subtraction base 10. The only difference is what we borrow. So don't borrow 10. Don't just write a 1 in front of your number to allow for borrowing, because that's not how it works when we're not working in base 10. We borrow whatever the base is. Next, we're going to look at multiplication. So multiplication can be performed in bases other than 10 as well. So in base 10, 4 times 3 means 4 groups of 3 units. In base 5, 4 times 3 in base 5 means 4 groups of 3 units again, but we can regroup these into groups of 5, which gives us 2 5s and 2 1s left over. So 4 times 3 base 5 is 22 base 5. We can place that on a chart. Of course, is that how we want to be doing all of our multiplication? Do we add things up when we multiply? Secretly, yes, that's what we're doing, but is that how we want to think about it? That would get pretty obnoxious with larger numbers, right? So essentially, it's going to become very helpful to have a multiplication chart in front of us. But again, just like with the addition, it was helpful to have the chart, but we're going to have to be able to produce the chart on our own, or do any individual multiplications on our own. So we ask the same questions. We say, okay, well, 4 times 3 is 12. 12 in base 5 is what? So this is 12 in base 10. So that's how many 5s and how many 1s? So it's 2 5s to get to 10, and then what's left over? 2. That's where the 22 comes from. So we're going to do the same thing for all of these numbers. Again, 0 times 0 is fine. 0 times 1, 0 times 2, 0, 0. All of these stay zeros. That's all well and good. In fact, any multiplication that gives us a number less than 5, it just works out the way we would expect it to, right? So all of these end up being the numbers we expect. 1 times 1 is 1, 1 times 2 is 2, 3, 4, 2 times 2 is 4, that's fine as well. But now once we get to 2 times 3, well, that's 6, right? That's 6 in base 10. So the question is, 6 in base 10 is how many 5s and what's left over? That's 1 5 and 1 left over, right? 5 plus 1 more gets us to 6, so this is 11. Then I'll carry this 22 over. 2 times 4 is 8. I'm running out of room here. This will be 8 in base 10. And again, I ask how many 5s and what's left over? 1 5, 3 left over, so this becomes 13. 13. 3 times 3 is 9. Right? 9 in base 10. How many 5s? There's 1 of them. And 4 left over gets us 14 here. And then 4 times 4 is 16 in base 10. How many 5s? Well, that one's a little bit trickier, right? It's not just one of them. So 5s, 1s. So we have to get up to 15. There's 3. And then 1 left over to get to 16. So this is, in fact, 31. So that's how we can make a full chart. So it may be easier to multiply the values in base 10 than change the product into the new base, like we did here. So you can make the chart, you can work with the groupings, you can do whatever works for you. Generally speaking, I'm just going to convert as we go instead of having the chart in front of me, since I'm not going to give you a chart to work from. So here we start by multiplying the first column the same way we would in any normal base 10 multiplication when we have multiple digits. So 3 times 5 in base 10 is just 15. Okay, so 15 base 10, what does that equal in base 7? So that's how many 7s, how many 1s? Well, it's 2 7s to get to 14 and 1 left over. 2 times 7 plus 1 times 1. So we write this as 21 base 7. Now we write a 1 below and we carry the 2, just the same way we would when doing normal multiplication longhand, right? So next we do 5 times 4, and what do we do with the carried 2 when we do multiplication? You have to remember how to multiply longhand in order for this to make any sense. We go 4 times 5 and we add 2. So 4 times 5 is 20, plus 2 is 22 in base 10. We convert, so 22 in base 10 is how many 7s and how many 1s? So it takes 3 7s to get to 21, and then there's 1 left over. So 3 times 7 plus 1 times 1, or in other words, 31 base 7. 3, 1. So now I write that out, and I write just the 3, 1 here, because there's no more places to carry the 3 to or anything like that. And now we go on to the next. So remember, the order of multiplying when we're working with vertical multiplication, like so, and then we go to the next one, multiply, multiply, and then if there was another one, we would do that as well, etc., etc. So in this case, we add a 0 in just like we would normally to sort of put a spacer here. And we do 2 times 3, which is 6 in base 10. 6 in base 10 is also actually 6 in base 7. Because it's how many 7s to get to 6? Well, there's none of them, right? No 7s, but 6 1s. So we have just 6. And so we can just place the 6 where we want it to be. right here. Again, adding this sort of space for the 0. Then we go on to 2 times 4. 2 times 4 is, of course, 8 in base 10, but what is it in base 7? Well, we get 1 7, and then what's left over? 7, 1 left. So 1, 1, in other words, 1 times 7 plus 1 times 1, that's 11 base 7. So we can just place our 11 here, and then we have to finish by doing the addition. And we do the addition, we have to remember we're still in base 7, the same way we were when we did the addition, previously in this chapter. So I add, again with that 0 there, I add 1 plus 0 is 1. 1 plus 6 is, well, it's 7, but we don't write 7 because we are in base 7. So 1 plus 6 equals 7 in base 10, which is 1 0 in base 7. So we will write a 0 here. Then we will carry our 1 to the next column and add 1 plus 3 plus 1. 1 plus 3 plus 1 is 5, and then we have our 1. So we have to remember what base we're working in when we do that addition. It doesn't become a normal base 10 addition problem. We're not done working in the base after we finish our multiplication step. So just remember that you need to convert as you go and keep track of any numbers that are the base or greater. So we can see our final answer is 1501. We can check this and all of that, but one thing to note, throughout all of this, even when we get to our final problems in division, notice that the final answer always has only numbers that are less than the base. That's going to be true no matter what. If you ever have a number that is greater than the base, that means you've done something wrong and you need to go back and check your work and figure out where did you forget to convert. Now for our last one, we look at division. So division is performed similarly to long division in base 10. A division problem can be checked by multiplication, quotient times divisor plus remainder equals dividend. So when we want to divide 3,410 in base 6 by 5 in base 6, we set it up like we would a long division problem. But essentially what we're going to need is we're going to actually need a multiplication table here. Because we know when we do long division, normally I would say, okay, well, how many 5s to get to, well, 3 first, but I can't get to 3. So how many 5s to get to 34? And in base 10, it'd be, oh, okay, well, there's 6 of them, right? And so then 6 times 5 is 30, and I subtract that off, and I get 4, and I go on, but that's not, that's in base 10. How many 5s is there in 34 in base 6? That's a little bit different. So it's going to be the same process, but we need to pay attention to the fact that multiplication is different here. So it won't be 6 times 5 equals 30. It's going to instead be part of our multiplication table for base 6. So we start by making a multiplication table. Now, I'm going to fill it all in, but we don't need this part of it. All we need is one row of it. So don't do more work than you need. I'm doing more work than I need just, for demonstration purposes. But the only part you need is this highlighted part. You need to know what 5 times 0 is. So 5 times 0 is, of course, 0. 5 times 1 is 5. But 5 times 2, now that is 10 in base 10. But what is it in base 6? So how many 6s, how many 1s? It's 1 6 with 4 left over. So that'll be 14. Then here we have 5 times 3 is 15 in base 10. So 15 is how many 6s? It's 2 6s with 3 left over, right? 2 6s to get to 12, and then 3 more to get to 15. Then next we have 20. So what is 20 in base 6? Well, it's 3 6s to get to 18, and then 2 more to get to 20. Then here's 5 times 5 is 25 in base 10. So how many 6s? That's 4 6s to get to 24, and then 1 left over. So altogether, yes, I filled in the whole chart, but again, you only need this highlighted row. Just do the one row, but I promise you want to do that row. You want to write this out for your notes before you start doing the division, or else you will get the division problem wrong. So now we start by asking the question, how many 5s until I get to 34 in base 6? So I look at my chart and I can figure this out easily. 32 is the highest number before I get 34, so there are 4 5s. So I put a 4 up here and I'm going to subtract off the 32. Because 4 times 5 in base 6 is 32 in base 6. So now when I do the subtraction, I also have to be careful to remember that I'm doing subtraction base 6. So if I do any borrowing, I have to keep track of that. I have to borrow 6s, not 10s. So in this case, there's no borrowing though. 4 minus 2 is just 2, and then 3 minus 3 is 0, so we're left over with 2, and we bring the 1 down. Now I ask the question again. So, how many 5s till I get to 21? Well, we look up here, and 14 is our number, right? So 2 times 5 is 14 in base 6. So I put a 2 at the top, and I'm going to subtract off 14, like so. So when I do that subtraction, I have to remember to borrow 6. So 1 minus 4 doesn't work. I'm not going to make this into an 11. I'm going to knock this down to a 1 and add 6 to the 1. So 1 plus 6 is 7. 7 minus 4 is 3. And now 1 minus 1 is 0. So we get 3, and I carry down the 0 from the top, and I repeat. So here, how many 5s till I get to 30? Well, there's 3 of them, because 3 times 5 is 23. So I put a 3 up at the top. I'm going to subtract off 23, like so. When I do that subtraction, once again, I have to do that same borrowing. So 0 minus 3 doesn't work out, but I can knock this down by 1, add 6 here. So 6 minus 3 is 3, 2 minus 2 is 0, and so we are left with this remainder of 3. Remainder of 3. So we say our final answer has a quotient 423 with a remainder of 3. And we can check our answer in the following way. Quotient 423 times, again base 6, times divisor 5 plus remainder 6. Does that in fact equal 3410 base 6? Well, we can check that doing our calculation for 423 times 5. We'll have to do some conversion and all of that. We do the multiplication and the addition in the same way that we would in base 6 as we've learned, and it will in fact come out to 3,410, but I implore you to check that to make sure you know how to do that multiplication and addition step.